have we chosen to use Postgres for every single example that we have seen so far? What makes Postgres so cool? That's what we're going to talk about today in this session. Here's the deal. When we talk about SQL, are we talking about one particular product? Are we talking about one particular implementation, one particular instance? Or are we talking about a standard which has multiple implementations across many different products? Well, historically, I would say that a lot of people were very concerned with what is standardized in SQL because there was a thought that we're going to migrate between different database products, and especially if these were commercial products, then you'd want to be able to say to the vendor, you know what, I'm not quite feeling your product, but I know that the work that you've produced is compatible with the work of some other vendor, and I'm going to switch over. These days, I'm not so sure. I remember back in the day writing a lot of code that assumed maybe I'm using MySQL, maybe I'm using SQL Server, maybe I'm using Postgres. I'm not quite sure. I'll make sure that I have the ability to switch later. But these days, unless I'm writing a library where my end users might have to make that choice, for my own code, I often have the ability to say, you know, once I'm decided to use Postgres, I'm probably going to use Postgres for the lifetime of this project. It's open source. It is very well supported. It's very mature. There's a large community. And I think it's fair for me to say, let's stick with Postgres and let's standardize on Postgres. Now, obviously, if I were deploying something to an end user and that end user might need to make their own choice, then I would need to retain that flexibility. But if I'm working on my own data and I'm building the system, including the database itself, then I think it's fair for me to stick with Postgres. Well, if that's the case, I have opened up the ability to use some Postgres-specific functionality because I no longer have to worry about, is this going to be compatible if I switch over to MySQL or if I switch over to MariaDB or if I switch over to SQL Server. And in our session today, I want to show you a couple of things which I think make Postgres a really neat tool to use. Some of these are features that exist in other database products. Some of these are features that are somewhat unique to Postgres itself. Whatever the case may be, this happens to be a collection of features which I think I like to use in Postgres, which will preclude me from taking the same code and switching over to, for example, SQLite, which has a much more restricted feature set, or MariaDB, which has a couple of features Postgres doesn't have, like temporal table support, but also is missing quite a few features that Postgres has, such as the very rich data types. As with all of the sessions in this series, we have orientated this session around 6 major questions, and so why don't I share my screen with you and we will jump right into it. This question is titled, How can I model arrays? Let's take a look. When I'm working with some data, it's often the case that I might want to represent not one data element, but multiple data elements. And so, for example, if my table is a bunch of people and their favorite foods, pizza, hamburgers, hot dogs, it's a very restricted view of what can constitute your favorite food, but that's what we're modeling here. I might model it like this. Each row is a person and their favorite foods. But immediately we can see that this is going to be extremely clumsy. Because if we were to suddenly decide that we want to eliminate hamburgers from this, we have to do some very clumsy string manipulation on each of these. And that string manipulation may itself be somewhat problematic because you can think pizza has many variants. You know, you could like New York pizza or Chicago pizza. And if one of these users like pizza, NY for the New York style pizza, we have to figure out some sort of escaping mechanism or some sort of encoding mechanism that makes it clear that this is 3 entries, not 3 entries, not 4 entries. And we can think this is going to be really clumsy really quickly. And if we think back to our discussion of normalization, it is very much the case that this is multiple non-atomic values that are being stored in the same row. And in our very first normal form, we might want to decompose this. And so the way we'll decompose this is we'll say each row stores just one preference for each user. Alice likes pizza, hamburgers, and hot dogs. Therefore, she has 3 rows. Bob and Charlie have more restrictive tastes, and they have the number of rows corresponding to that. And if we need to say that, you know what, nobody really likes hot dogs that much, we could delete from this, and we could cleanly delete this. We don't have to worry about this ambiguity in the modeling. We could even do something like select, how many people happen to, or for each person who likes what things, or even for everybody, what are all the foods they like. And if we look at this this latter query, we can see it's actually kind of like the very first query that we ran when we modeled this as a bunch of strings. In fact, we can even do a string join operation, an array to string operation, to take this new formulation, this new encoding of this table where we have atomic values in each row, and make the result of a query look exactly like the original formulation where we didn't have atomic values. And so if there was a reason that we wanted to have one row per user with a comma separated value, maybe we're just printing this to the screen, we could do that. And we could do that with simple array operations in Postgres. However, what if it's the case that we don't want to model just your favorite foods, but the order of your preferences? Because between you and me, I know some people who might say their favorite foods include pizza, hamburgers, and hot dogs. I don't know a single person who, given the choice, would say, I'd like to go for hot dogs. I'd like to go down the street to the dirty hot dog stand where they reach their hand into the water, swim around a little bit and pull out the hot dog, as opposed to going to a very nice restaurant or even a fast casual restaurant to get a hamburger. And so we're going to model not only what their preference is, but the priority of their preference. And so in this table, we have some priorities. But probably it's the case that for these priorities, we want to model more than just a zero value. We want to be able to set somebody's priority for hot dogs a little bit higher and see what happens. Or we want to ensure that the priorities are unique. In other words, that you can't have multiple choices. There is some tie breaking. You have a ordered selection of which foods you like in which order. And one of the ways that we can ensure the uniqueness is via a unique constraint on this table. So we could say for each person, they can only have one 0th choice, one first choice, one second choice. That's all that's possible. But you notice that there's another anomaly that might be present here. Bob doesn't have a 0th choice, and Charlie doesn't have a first or second choice. Charlie only has a 3rd choice, which means that this user, I guess their 0th first and second choice is nothing. I'm not quite sure. And so another constraint that we might need to model is that these priorities strictly start from some value and end with some value, and they don't have gaps. You can't have a 5th choice if you don't have a 0, 1, 2, 3, 4, or 1, 2, 3, 4 choices in front of it. How do we model that? Well, if you think about it, there's no way that we can model this with something like constraints, because constraints are modeling on the tuple level. They're modeling each individual row and a constraint on that row. And the constraint that we want is across multiple rows. We see some characteristic, like if you were to insert a 3, then you must have a 0, a 1, and a 2 already in that table. But what we can do is we can write a trigger. And that trigger can go into the table and select what's in that table and check to see if you're going to insert a row which contains 3, that you have 0, 1, and 2 already there. And here we can see with the exact same data, this attempt to insert this row for Charlie, where the priority did not match what the table should already have, doesn't actually succeed because the trigger prevents it. And if we raise an exception here, we could even prevent the entire query as a whole and say, look, you can't have a 3rd choice unless you have earlier choices as well, a 0th choice, a first choice, and a second choice. So we can do that. But the moment we do that, a question arises. What if somebody changes their priority? What if Alice suddenly decides that she wants hamburgers more than she wants pizza and she wants to swap those two? Well, a problem arises because we have to do this as 2 separate updates because each update can only affect one row at a time. And each update is going to transition the table from a valid state to an invalid state because here, as of this update, we have 2 rows that'll have priority 1, and then as of this update, okay, then it'll be fine again. But what that means is we would have to figure out a way to temporarily suspend the trigger and the constraints until we're done doing some aggregated set of options that shuffle things around. And it is very easy for this query to fail, but this query not to fail, so we'd have to put this into a transaction. It's very easy for us to even forget to do something like this and to leave this table in some uncertain state. So there's something missing about this modeling. When you think about arrays as a data type in SQL, one of the use cases that they allow you to solve, and they allow you to solve in a way which is otherwise very tricky to do, is vectors of preferences. strictly ordered elements where there must be a first element and a last element if there are any elements at all. And what you can think is, if I went back to a modeling that looked not too dissimilar from what I started with, and instead of storing these as strings, I stored them as an array of values, and I stored that as a single column, not as multiple rows. Well, the thing about that array is the array implicitly has an ordering. The array implicitly says the 0th element, the element at the very beginning, is the most preferential and the element at the end is the least preferential. And the array says there's no tiebreakers. This is, a strict linear ordering where every element follows another element. And because Postgres has array manipulating and array selecting functions, we can do things like select all the users who happen to like pizza, or select all the users who happen to like pizza and hot dogs. And note that this is a query that is looking for membership, not necessarily for a particular ordering of things, because you can see it selected Alice, who had pizza and hot dogs, but at 2 different positions. If we did this, then we could actually do something interesting, because we can do some array manipulation functions. Now, if you're a Python programmer, I need to specify one very important thing about how Postgres arrays work. They start indexing from 1, not from 0, and slicing of these things is a closed interval. It includes both the starting point and the ending point, unlike in Python where slicing doesn't include the ending point. It is a half open interval. And so here we could select just the second and the third element from Alice's preferences, or we could select the second and the third element and the first element. We could shuffle these elements around. And so what we could do is we could very easily, within one query, take values like A, B, C, D, E, F, and say, well, move one of these values to the end by selecting via some slicing syntax all the values up to some point, then the value itself, and the values to some other point. And so here you can see I'm just reconstructing the original array, selecting all the way up to but not including the 3, then the third element, then the third to the end. Or I could select the third, then the third and the fourth, and then the fourth to the end. Or I could select up to the third, then put the fourth element, and then put the third element, and then the fourth to the end. I can do swaps, and I can do them in a single expression. Meaning, I could use this mechanism to, in a single expression, swap the ordering, which was a very tricky thing for me to do with the former modeling. And I could even do this with a set expression. I could say set x's of 3 equals x's of 4, and x's of 4 equals x's of 3, and it does exactly what I expect. It will actually swap the third and the fourth value, A, B, D, C, E, F. And if I want to insert something, I can even insert something by just updating to include an extra element. And this is where those isolation levels and that transaction knowledge is going to be very important. Because you could say if 2 people are inserting at the same time, what should happen? That is a very big question. And we would say in this modeling, one of them is probably going to clobber the other one. So we have to be a little bit careful, where in the previous modeling, we don't. But we'll leave that aside and say at least, at the very minimum, we can do operations that are otherwise very tricky to express, like removing elements or slicing out elements or rearranging elements. However, this is still not in that first normal form because we have that array. And so multiple simultaneous users will clobber each other. We have to be aware of that. And we don't have atomic values on each row. And if I were to try to normalize this, one way I might normalize this is to try to jump ahead to our second or third normal form. And what I might do is I might say, let me represent the people all by themselves. So if somebody's name changes, I can change that on one place, one source of truth. So I'll represent the people as one table. I'll represent the food as one table. So if the food name changes, or if there's other parameters associated with the food, like the caloric count or the varieties that are available, I can change that in one place. And I could represent the preferences as a join table, which takes the people and the food and then references each person against each one of the foods. And that maybe eliminates some of the limitations of this non-atomic modeling, except here's one thing that Postgres doesn't do that the SQL 2016 standard actually specifies. In the case where we're creating this join table, we would want to have each of these persons reference the people in the people table, reference each one of those elements, so that we can't have a join row where, for example, we specify a person who doesn't exist. We would want the same thing for the foods table. But we cannot put a reference to a foreign key on the elements of an array. But even though SQL 2016 says you should be allowed to have arrays of reference types, this is something that has been worked on in Postgres for some time. It's still some time away. The syntax for it would look something like this when it's implemented. You'd set a foreign key for each element of foods. But as of today, you cannot set a foreign key that ensures that this is a consistent schema if it's a foreign key on an array of elements. In some point in the future you could, and of course you could always write some kind of trigger to make sure that this works. Although of course whenever you're writing these kind of triggers you do have to be very careful because those triggers, one, they do introduce a little bit of slowness on insert and update operations, and two, they can be a little bit tricky to write. The syntax can be a little bit clumsy. One way around this, however, is you could say by construction I can make sure this is correct. So maybe I don't assert the constraint that if I reference a food in this array, that this food exists somewhere else. Maybe you just leave that unconstrained without any foreign key relationship, and then you use some sort of join, some sort of directional left or right join to just eliminate any cases where there's something missing. That could be a possibility for what you could do to get around this. And if you were to decide that you're willing to live with the ability or you're willing to live without this constraint here, even though you probably should constrain this, well, you can see that we can construct a query that actually gives us back what the original table looks like. We could select, or we could insert into this, every one of our original users, and we can generate a fairly large, fairly long query that here's our preferences, here's our people, here's our food. Well, we can do some inner joins like this, except this inner join doesn't work because one of these tables has an array element, but Postgres has our back. We can always unnest an array. We can see that whenever we're working with arrays in Postgres, we're oftentimes aggregating rows into arrays and disaggregating arrays back into rows. Here you can see we're starting with the pre-aggregated 1, 2, 3 single array as a single row value, but we can unnest this to turn it back into that other formulation. So you can see the two formulations are not that different. And we could do this in some sort of CTE in order to do the join, in order to get back to one of the formulations that we had talked about before. If we like it in this formulation where we have one row per entry, we could do that. And this could be a view that we then select from and we make sure that we eliminate nulls, or we could even do something like this. We could do something like array ag to aggregate these and then group by the person's name, so we get that. Or if we really wanted to, we could do array to string on the array ag and turn this back into a string. Whatever the case may be, I want to share with you that one of the features that I really like about Postgres is the ability to represent these sort of compound array values in single rows, because there are many cases where this is incredibly valuable. Anytime I need to represent some sort of ordered structure, it can be tricky to do that with updates in raw SQL, or anytime where the element itself has some compound nature and it has pieces and the ordering itself is piecewise, like a path you could think of is an ordered collection of each one of the steps in that path.